Hello and welcome again to my Physics Online video lecture supplement series. In today's video, I wanted to look at part 3 of my lecture on dynamics, forces, and motion. In this part, we discuss drag forces. So drag forces are most commonly associated with stuff such as air resistance, although we also can include things like the force that is applied to an object that's falling through water, for example. Basically, a drag force is any force which is acting on an object that is moving through a fluid. So a fluid is anything like a liquid, a gas, or a plasma. And what a drag force basically does is it opposes the motion of an object relative to whatever fluid it's moving through. And it does so in a way which is usually proportional to some function of the speed of the object relative to the fluid. What that basically means is that as the speed increases, the drag force will also increase. And I write that it is some function of the speed because in some cases the function might be linear, in which case the drag force basically looks like F equals negative B times V, something like this. Sometimes the function is quadratic, so the drag force is proportional to the square of the speed, etc. And drag forces are a type of resistive force, which means that they tend to slow the object down, though it's not necessarily true to say in this case that the drag force will always slow the object down. Instead, it can sometimes just reduce the object's rate of acceleration, as we'll see in a minute. There's two types of drag forces that I want to look at today, and the first of these two is basically applicable to large, fast-moving objects that are passing through a relatively low-density fluid. The typical function that goes with such a drag force is that the drag force is half of some drag coefficient times the density of the fluid times the cross-sectional area of the object times the object's speed squared, where this speed is with respect to the fluid. And basically, what this applies to is an object which is much more dense than the fluid through which it's moving. So, for example, if you take a rock and toss it through the air, the rock's density is a lot greater than the density of the air. The rock might have a density of, say, 2,000 kilograms per cubic meter, or 4,000 kilograms per cubic meter, or so on. The air has a density of about 1 kilogram per cubic meter. So it's a very, very large difference. This is not applicable usually if the object's density is comparable to the density of the fluid. So for example, if you toss that same rock into water, where the density is more like 1,000 kilograms per cubic meter versus the rock at 2,000, 3,000, 4,000, whatever. This means that this equation is not going to apply in that case. So we're looking at a very fast moving object passing through a very low density fluid. And this diagram over here to the right is basically a picture of what the motion might look like. And what it's showing is, suppose that you drop the object from very high up. And so obviously if the initial speed is 0, we're not really in a fast moving part of the motion yet. But what's going to happen is you're going to have some acceleration downward thanks to gravity. And so the velocity basically is going to increase, and that's why this thing is getting farther apart as the velocity is basically increasing, speed's getting faster. So you could think of this as sequential pictures taken, say, a second apart, or maybe 10 seconds apart. And what the purple arrow is showing is what would the net acceleration look like in this case, because you still have a downward acceleration due to gravity, but you also end up having some upward force from the drag that's acting on this object. And so initially, when this thing is very slow moving, that drag is minimal, and so you might have almost no change. Then as the object begins to fall, you see that the velocity is increasing here. The red one is the velocity increasing. The purple one is the net acceleration. That purple arrow is decreasing as it falls because the drag force is getting greater. And so at some point you hit what's called terminal velocity, at which the drag force is equal to the force of gravity plus, if you want to include it, the buoyant force upward on the rock or object, or whatever your object is. So at this point, you're in the terminal velocity regime. The speed is basically constant and there's no acceleration in any direction. All right, so we should include a few drag coefficients because you might want to actually do a calculation with this. So you need to know basically a fluid density, and you need to know a drag coefficient, and you need to know a cross-sectional area and a speed squared in order to get the drag force. And so here are a few drag coefficients which I've pulled from a table in the OpenStax general physics text. And these coefficients are actually usually determined empirically. The usual way of doing that is to build like a wind tunnel and then put the object in the wind tunnel and basically increase the wind speed or decrease the wind speed with respect to the object and sort of measure what kind of force is on the object. The coefficient itself is actually dimensionless. So this is force that's in newtons, that would be in kilogram meters per second squared. So this thing right here is in meters, is in kilograms per meter cubed. This right here is in meters squared, and this is in meters squared per second squared. So let's do a little dimensional analysis. So this one right here, again, that's in newtons, which is the same thing as kilograms meter per second squared. So if we want to find the units of C, we basically would do C has units of FD over rho A V squared. So we could do like as proportional to this, for example. So rho has units of density, so that's kilograms per meter cubed. A is an area, so that means that it's in meters squared, and then V is in meters per second. So this right here is basically saying kilograms times meters per second squared divided by kilograms per meter cubed times meters squared times meters per second squared. So we can see that the kilograms cancel here. There's a meters cubed right here and a meters squared right here. And this is an over, so this so far can reduce to meters per second squared divided by 1 over meters times meters squared per second squared. So this 1 over meter can cancel out this, and then this meter right here would cancel with this meter, and we're left with over second squared and over second squared, and so that is unity. So no units. And so that's why this drag coefficient has no units to it. The coefficient of drag, or drag coefficient, can actually depend on the velocity, but for simplicity we're going to assume that it's constant as per our table. And this topic of drag, in particular drag on a dense object moving through a sparse medium, is actually of interest to quite a few different industries, everybody from the folks who try to do athletic wear, like the outfits people are wearing while playing hockey, or especially while playing in a sport where you're trying to race, to race cars, to just simple auto industry. After all, if you've got a large drag, then you're going to tend to have less fuel efficiency. So if you're trying to make a really fuel efficient car, you might want to make it have lower drag. And then of course the aerospace industry is very interested in this, since it affects not only how fast can you make your plane go, but also you can change the drag and use that as a method of air braking, for example, or even some types of maneuvers. So what I want to do now is look at how we can obtain the terminal velocity. And again, the drag force is opposing the motion of an object which is falling through a fluid. It is a force, which means that we can apply Newton's laws. And so specifically, we're looking at Newton's first law and Newton's second law here. And of course, the start to Newton's laws is to add all the forces that act on an object. So since the object is moving through a very low density fluid, we're going to ignore the buoyant force for now. The buoyant force actually can be treated as just a modification of the weight of the object, and it's going to be pretty negligible. In any case, you get that if you ignore the buoyant force, you get that the weight of the object plus the drag is all the forces acting on this object. And so as the object is falling, this drag force, which is a resistive force, is actually increasing. And at some point you get to where these forces are balanced, and at that point there's no force on the object. That means you're in Newton's first law regime. That means that you have zero acceleration, and you basically have reached the terminal velocity. So the net force would look like this when you put in the gravity and when you put in the drag. Again, you can modify this term by adding an additional constant for the buoyant force, but it's going to be a very small modification. Basically, you can do that by treating the mass of the object as the volume times the density, and so you'd end up having essentially the volume of the object times the density of the object minus the density of the fluid times g. So in any case, you keep speeding up until you hit that terminal speed, and basically that's what happens when the drag force and the force of gravity, or the force of gravity minus the buoyant force, is zero. So you set mg equal to drag force, and you can then solve for what the speed needs to be for that to happen, since the drag force is proportional to the speed as per this equation. So in other words, we're essentially solving the speed in this equation, and then we're setting this term right here equal to gravity. And so imagine putting an mg right here and solving for v. So what that looks like, we're looking at the case where the sum of forces is zero. So that is mg minus fd is equal to zero, or in other words, fd is equal to mg. But fd, the drag force, is 1/2 times c times rho times a times v squared. So basically the terminal velocity case, we use vt. So vt squared times 1/2 times c rho a should be equal to m times g. And so vt must be square root of m times g times 2 divided by c rho a. And if you wanted, again, to modify to include the buoyant force, so with buoyant force, you would use a slight modification to this mass term. You basically have mg minus fb minus fd is equal to 0. And the buoyant force is something that we're actually going to discuss later, so I don't want to get too much into that here. But you could just basically imagine putting in a minus FB right here in this equation if you want to include the buoyant force. In any case, this is therefore what you get for the terminal speed. And of a special relevance in here is you can't really change most of the things, most of the terms in this equation. You can maybe change the drag coefficient by changing what the shape of the object is that's passing through the fluid. And then you can actually change the area as well. So for example, when you're parachuting, you basically are changing both the shape of the object, and more importantly, this parachute has a much larger cross-sectional area than the person does. And so basically what a parachute is doing is it is decreasing what the terminal speed needs to be. And so that is, it basically means that this guy will fall at a slower ultimate speed than he would have if he had no parachute. And that's why the parachute basically lets you jump safely from a plane. Is you have this large cross-sectional area. That means that you have a slower terminal speed. It means that you're moving a lot slower when you hit the ground, and so as long as you hit the ground correctly, then you basically land safely. You don't break your legs, you don't hit at a fatal speed or anything like that. And so that's what the use of these parachutes is. I mentioned that there were two types of drag that I wanted to look at. So we've already looked at the first one. The second one is basically the Stokes Law Drag. And the Stokes Law Drag is specifically for a small, slow object which is moving through a denser medium like water. And so for the Stokes drag, you actually get a Stokes Law equation that looks like this. So the force is 6 pi r times eta times v, where eta is actually called the viscosity of the fluid, and r is the radius of the object. Note that this is more akin to something like this metal ball falling through water, because the metal ball has a density that is not many times the density of water. In fact, it may actually only barely exceed water depending upon what you have inside of the metal ball. It may in fact be less than the density of water. Stokes' law is going to assume a spherically shaped object, and we might generalize Stokes' law a little bit by saying that the drag force is equal to some constant b times the velocity, and it's negative because it's going to be in the opposite direction as the velocity. So in specifically Stokes' law case, b would have a value of 6 times pi times the radius of the object times the viscosity of the fluid. You can again solve for the terminal speed of the object in this case, and again you can basically use the force of gravity, the buoyant force, and the drag force. You add all those things together, you get the mass times the acceleration. The buoyant force in this case may actually not be negligible, but again, I already showed that the buoyant force is just going to be some modification of the gravity term. And so the terminal velocity you can get by basically solving this equation. The drag again is negative b times v. So you have mg minus bv equals ma. And so a, you're basically solving for a, is going to be g minus bv over m. And the terminal velocity occurs when you have no acceleration. So you plug in a 0 for the a and solve for the terminal velocity. You come up with something like this, where again this mass might be modified by the buoyant force if it's not negligible. And in fact, a lot of the time it won't be. For example, if you have a higher density fluid. And what this basically looks like, by the way, in the higher density fluid is that the velocity will be increasing, but it will be increasing like 1 minus some exponent to a negative power. So what that looks like is the speed actually is going to look like mg over b times 1 minus e to the negative bt over m. So this right here collectively is actually going to be equal to the terminal velocity times 1 minus e to the negative t over tau, where we have set tau equal to basically m over b. So this is the rough approximation for what v would be. You can, of course, modify it because m is really the volume times the density. And so actually, if you want to include the buoyant force, then m becomes volume times density of the object minus density of the fluid. Other than that, everything else basically stays the same. So this right here is basically showing what that equation for speed looks like. Is basically increasing, but the rate at which it's increasing is slowing down. And so at some point it hits this terminal velocity. In fact, it's actually asymptotic to the terminal velocity. So to close out this lecture, let's work a few simple examples. First example is that we have a drag force which has acting on a ball that has a given cross-sectional area. It's moving through an air with a given speed, and we have an approximate density for air. So the question is, how much drag force is going to act? All right, so this drag force, since we're using some ball and it's got some cross-sectional area like this, is moving through a low-density fluid, we're basically looking at that the drag force should be 1/2 times c times rho of the fluid times the cross-sectional area times the speed squared. So the thing that we need to get is this value of the drag coefficient. So to do that, we might return to this table in our notes or in the OpenStax textbook. Since it's a ball, it probably means that the object is a sphere. So that means that the drag coefficient has a value of about 0.45. So that means that what we have is 1/2 times 0.45 times 1.2 kilograms per cubic meter times the area was 75 centimeters squared. So that's 75 centimeters squared times 1 meter per 100 centimeters quantity squared. So kind of need a big parenthesis for that, times 60 meters per second squared. So this definitely calls for some calculators. So let's go 0.5 times 0.45 times 1.2 times 75 divided by 100 divided by another 100 times 60 squared. And we get 7.29. 7.29 what? Well, it's a force, and we put everything in meters, kilograms, and seconds, so this means that the drag force is about 7 point, looks like we have two significant figures, so 7.3 newtons in this case. Our next question was, what's the terminal speed of the ball described in the example above? So let's assume that the ball's mass is a kilogram. All right, so we have that the terminal speed is generally given by the equation V is square root 2 mg over rho c times A. So again, we looked up the value of c from that table in our notes. C was 0.45. The density, again, from the previous problem was 1.2 kilograms per cubic meter. That's the density of air. And again, the cross-sectional area was 75 square centimeters. So the area is 75 square centimeters. Might as well just convert that. So that's got to be times 1 over 100 centimeters, 1 meter per 100 centimeters, and that's squared. So we have 0.75 over 100, or that is area is 0.0075 cubic square meters. Okay, so the terminal speed, therefore, this is a terminal speed equation, should look like this. Square root of 2 times 1 kilogram times 9.8 meters per second squared divided by 1.3 kilograms per meter cubed times 0.45 times 0.0075 meters squared. Okay, so now we plug that into the calculator. All right, so 2 times 9.8, I'm not even going to bother putting in the times 1. So now we're going to divide by 1.3, going to divide that by 0.45, divide that by 0.0075. Okay, and now we take a square root and we get 66.84. So the terminal speed here is about 67 meters per second. Okay, gut check. Does this seem like a reasonable number to you? Well, one way of checking the reasonableness is thinking, okay, so does it seem like a ball should be able to keep falling until it hits that speed? Well, 67 meters per second is about 150 miles per hour. So that's a bit faster than a fastball, for example, in baseball. Like a very, very fast fastball in baseball is only like 100 miles per hour. So this seems like a reasonable scale for that. It's worth noting, by the way, that you can have an object which is moving at a speed that's faster than the terminal speed. For example, very often like a meteor will hit the Earth's atmosphere moving faster than the terminal speed for the atmosphere. And basically all that means is that the object will start slowing down until it hits the terminal speed. So instead of having some velocity versus time graph that is speeding up like this until we hit the terminal speed, you end up with velocity versus time that maybe slows down like this until you hit the terminal speed. All right, last question. Let's say that we have a bacterium which has a 1 micron radius. We'll say that the bacterium has roughly a spherical cross-section. At least if it's falling downward, it could hypothetically have a spherical-esque cross-section. So given that water has a viscosity of 89 millipascal dot S, that's millipascals per second, what's the Stokes drag force on a bacterium whose speed in the water is 1 millimeter per second? This, by the way, may look like a very strange unit to you. A millipascal times a second is, well, basically Pascal is a unit of pressure, and that's force per unit area. So this is basically force times seconds over meters squared. So let's go ahead and try to solve this one. All right, we're specifically told that we're looking for a Stokes drag force. So that basically means that what we're going to do is use this Stokes equation. So Stokes equation says that the drag force should be 6 times pi times the radius times the viscosity times the speed. So what we need to do is convert everything into common units so that we can get a force in newtons. So the radius is already given, is 1.0 times 10 to the minus 6 meters. The viscosity was given as 0.89 millipascal dot second. That is basically going to be 8.9 times 10 to the minus 4 Pascal dot second, which is the same thing as 8.9 times 10 to the minus 4 Newton times second over meters squared. So there's where our newtons are going to come in. And then last but not least, we have the speed, which was 1 millimeter per second. And so that's going to be 1 times 10 to the minus 3 meters per second. So this means that our Stokes force is going to be 6 times pi times 1 by 10 to the minus 6 meters times 8.9 by 10 to the minus 4 Newton seconds per meter squared times 1 by 10 to the minus 3 meters per second. Okay, so whip out that calculator. And what we have is 6 times pi times 8.9. And so that's 167.7 whatever. We're going to end up with only one significant figure anyway because of the speed. So let's call this approximately 200. And we had a times 10 to the minus 6 minus 10 minus 13. So 10 to the minus 13 newtons. And so basically this is saying that the Stokes force is about 2 times 10 to the minus 11 newtons, which makes sense because we're talking again about a bacteria. Bacteria doesn't really weigh very much either. So basically this thing might be falling, but it's going to fall fairly slowly through the water. All right, so that's all I have for today. And before I sign off, I just wanted to sort of give credit where credit was due by showing really the credits, or if you will, the references for this video. This is largely the sources that I took these various diagrams from. Of course, we are using the OpenStax textbook as the main book in our general physics class and the supplement in the introductory physics class, so they especially deserve extra credit for that. And so thanks for watching, and I hope you found this video helpful.